Hi everyone, my name is Nikos Giavellis and I'm here with Nofar Karmeli to present to you our work on the orders of conjunctive query answers that allow efficient direct access. This is joint work with Wolfgang Atterbauer, Benny Kimmelfeld and Mirek Riedewald. So let's start with an example.
Hi, Nikos. I have these tables with information about my employees. Which employee had which role, how much I paid a role in a specific period of time, and how much I paid them for their travel expenses according to where they live. Now, I would like to get some statistics about how much I pay an employee a month, like the median, the box plot, or all of the details in pages that I can go through freely. One way of doing that is to compute the join of these relations, which can be described in this query here. And then I'll get all of the query answers, which will tell me how much I paid an employee per period of time by just summing these two numbers. And I can sort all of these answers by the salary plus the travel expenses, and I'll get direct access to anything I want. The problem with this is that it can take very long because the number of query answers here can be much larger than the size of my input. So is there a way of doing this without materializing all of the answers?
That's a very interesting problem, Nofar. So let's try to formalize it. Let's call it the direct access problem, which has also been called the random access or the jth answer problem in the literature. This problem is about a specific query, and the input is a database of size n. The goal is to design an algorithm that after some pre-processing takes the index k on the array of query answers and is able to return the answer in that particular index. Now, since you require also a specific ordering, let's add that to our problem here, forcing the array of query answers to be sorted by that order. Our goal is to find an algorithm that has quasilinear preprocessing and polylogarithmic access time, because linear preprocessing is unavoidable anyway, and logarithmic factors do not have much of an impact in practice. So what are the orders you would like to support?
Well, there are two orders that I can think of that sound interesting. One of them is a lexicographic order, meaning together with the query, I will give you an ordering of the free variables, and I would like all of the answers to be sorted, let's say first by address, then to break ties by salary, and so on. But then sometimes I don't care about all of the attributes for the purpose of ordering, and I can give you a partial lexicographic order that just has an ordering of some of the attributes. Another interesting order is what we saw in the example before, sum of weights, where the domain values of variables have weights, and we want to rank the answers by the sum of the weights.
What is the connection between these two?
Well, sum of weights is a stronger requirement than lexicographic because we can use sum of weights to simulate lexicographic ordering. For example, if we want to get these answers sorted first by address and then by salary, we can assign the weights in such a way that address always dominates the weights of the salary, and so sorting by the sum of their weights is equivalent to sorting first by address and then by salary.
Okay, let's look at some of the related work. I know there has been work on enumeration, where the task is to return the query results in order, one after the other. And this task is similar to direct access because we first access the first index, then the second index, and so on. It has been shown that with or without a ranking, enumeration is possible with logarithmic delay if and only if the query is free-connex, which is a particular requirement on its structure. I know there has also been work on direct access, right?
Right. So there has been previous work on direct access, and all of these previous solutions that we see here produce the answers in some lexicographic order, whether they state it or not. But this lexicographic order is restricted by some structure, for example, a join tree. And we would like to support additional orders and to identify exactly which orders can be supported, which was not done in previous work.
Why don't you remind everyone what the free-connex query is?
A free-connex query is in particular a cyclic, and a cyclic query has a join tree, which is a graph that describes the query where there is a node for every atom. This graph is a tree, and if we consider every variable separately and we look only at the nodes that contain these variables, then these nodes are connected. Now, free-connex queries have an additional requirement, which roughly means that the free variables of the query are connected, meaning they appear together in a part of the tree. So Nikos, why don't you tell everyone what we found out when we did this work?
Yes, so we have the complete picture for direct access, and our lower bounds have some assumptions that are common also in enumeration, namely no self-joins and some hypothesis in fine-grained complexity. So within the class of conjunctive queries, we have the free-connex ones, which, as we saw, anything outside that class is already intractable for enumeration, so we can't hope to have direct access. Now, within the class of free-connex queries, we establish a dichotomy that depends on two conditions. One of them is L-connex, and the other one is a disruptive trio, and we will see what that is later. For the sum of weights orders, the tractable cases are much more limited, and it's basically only the queries that are acyclic, and also their free variables are contained in a single atom. So Nofar, why don't you go ahead and explain the lexicographic part?
Sure. So for lexicographic orders, we have a dichotomy. Given a conjunctive query and an ordering of the free variables, we can achieve efficient lexicographic direct access if and only if, in addition to the query being free-connex, we have no disruptive trio. Here we should mention that the lower bounds use the same assumptions as the one we have for the dichotomy for enumeration. Now, what is a disruptive trio? A disruptive trio is three variables, such that if we look at the last variable in the ordering we want out of the three, it shares atoms with the previous two variables, but the previous two variables do not share an atom between themselves. For example, this query here, Q2, if we want the ordering V1, V2, V3, has a disruptive trio, so it is intractable. But if we swap V2 and V3 in the body of this query, we get Q1, which has no disruptive trio, so it is tractable.
I see, and that is for full lexicographic orders, where you have all the variables in the ordering. For partial lexicographic orders, can't you complete them into a full lexicographic order and use the same?
Right, so the positive side extends the way you said. If we're interested in a partial lexicographic ordering and we can find a tractable completion for it to a full order, then we can solve this full order and get in particular the partial order we want. For the negative part, it's not that evident. We need to show that it's not possible to solve the partial orderings in a different way where the ties are not broken in lexicographic order. And indeed, this is what we show. We show that all tractable partial lexicographic orderings can be achieved using a completion to a full order. So the dichotomy we get is similar to what we had before. And here we identify the partial orders that can be completed to a tractable full order. So we're given a query and an ordering of some of the free variables. And to achieve partial ordering, in addition to the requirements we had before, we need the query to be L-connex, where L is the variables that we care about the order of. What is L-connex? It's very similar to free-connex. So for free-connex queries, we said that we want a subtree of the join tree that contains exactly the free variables. And for L-connex, we also want a subtree that contains these variables that we care about.
I see. And how do you prove the lower bounds?
Let's take as an example this query we saw before, Q2, that has a disruptive trio if we're interested in the ordering V1, V2, V3. we use the same assumptions as we use for enumeration. In particular, we can assume that Q1 is hard. Q1 is the same as Q2, but where the third variable is projected. And Q1 is equivalent in a way to Boolean matrix multiplication. It is acyclic, but it is not free-connex, so it is known to be hard. And now we have a reduction that tells us if we assume that we have efficient lexicographic direct access to Q2, then we can enumerate Q1 efficiently, which is a contradiction. Now, these are the answers to Q2, sorted the way we want. How do we use it to enumerate the answers to Q1? Well, we first access the first answer, and we only print the values of V1, V2. Then we use binary search to reach to exactly the next answer that has different V1, V2 values, and we print that. And we continue this way. So we have a logarithmic number of direct access calls between every two answers, which means that we answer Q1 with a very efficient delay, which is a contradiction.
I see. And what about the positive side? How does the algorithm work?
For the positive side, we built upon a previous approach that was presented in PODS of last year. This approach says, given a free-connex query, we reduce it to a query where all of the variables are free and it has a join tree. And we use this join tree to give us some hierarchy between the input relations. We have a pre-processing phase that goes bottom up on the tree and performs some dynamic programming that computes some aggregates. And then the access routine uses these aggregates to recurse down the tree. So we're given an index we want to access. We use the aggregates to choose a tuple from the current relation. We use this tuple to filter the children. And then we have some computation that tells us how to split the access task into the children, and we recurse down. So the ordering we get is this ordering in this case, where we first get the first answer of the left subtree together with all possible combinations that match it in the right subtree, and then we move on to the next answer of the left subtree. Now, with this previous approach as is, there are two problems. The first problem is that the order we get is determined by the tree we use. And our solution is we define trees that are specialized to specific orders we want to achieve. In particular, we call them layer join trees, where every layer is a node. And if we introduce the layers one by one, we introduce the variables we want to achieve, the free variables, in the order we want to achieve. We show that if there is no disruptive trio with respect to some order, then we have a layer join tree that matches that order. The second problem is that because of the nature of the access routine that divides the problem into independent recursive calls between the branches, the ordering we get is some sort of depth first order. And using the same access routine, we cannot support any order given by a layer join tree. This is why we have a modified access routine that allows us to inject information between different branches of the tree.
For sum of weights orders, we similarly establish a dichotomy where we show that tractable queries are exactly the ones that are acyclic and there is an atom that contains all the free variables. For example, Q1 here has the free variables x and z in the R atom, while in Q2 those variables do not appear together. And for the easy cases, it is trivial to provide direct access.
Why is it trivial?
Because we can find the query answers in a single relation. So if we filter that relation and sort it, it is very easy to provide direct access. For the hardness proofs, the main observation is that with binary search, we can find a specific weight. So we use the three-sum hypothesis, which says that for three sets of integers a, b, and c of size n, we can't find a triplet that sums up to 0 in time n to the power of 2 minus epsilon. For the reduction, we use two independent free variables, where these are variables that do not appear together in one atom. And so they can independently take all the values of A and B. And now, if we look at the query answers, the weights are all the possible pairwise sums of A and B. So now if we want to find a triplet that sums up to 0, we can use binary search to search for minus C for all possible C's. So this concludes direct access. And we saw that for sum of weights orders, the tractable cases are very limited.
So you say there are many intractable cases. Are these cases intractable because we require to support multiple direct access calls after one preprocessing, or is supporting one direct access call already hard?
That's an excellent question. So let's define another problem to look into it. For direct access, we saw that the preprocessing phase constructs a data structure that then supports multiple accesses efficiently, and each access only takes polylogarithmic time. Now, for the problem of selection, there is no preprocessing, and we simply count the time it takes to access a single answer. Tractability here is defined as n polylog n for one single access. So we similarly establish a dichotomy for selection on the class of full conjunctive queries, where we show that the tractable cases are exactly the ones that have two maximal atoms. So here Q1 has two maximal atoms because T is absorbed by S, but for Q2, none of the three atoms is absorbed by each other, so the query is intractable. For the tractable cases, we view the query answers as a matrix. So for this example query here, we have this join on attribute y, which gives us a union of two matrices, one for each join value, D and E. And now if we also sort the input relations on their weights, every row and column of the matrix is sorted. And this allows us to use a known result from Frederickson and Johnson, which says that selection on a union of sorted matrices can be done efficiently.
So you said that this query is tractable for selection, but before we showed that if we want the lexicographic order X, Z, Y, there is a disruptive trio, and so it was hard for direct access.
Right. For this query and order, direct access is intractable, but because we established that sum of weights can simulate any lexicographic order, this implies that selection is in fact tractable here. For the intractable cases, there are multiple cases. One of them is the three-path query, where we use a reduction from the Boolean triangle. The query answers to the three-path query are a superset of the answers to the triangle, so we want to identify the ones that also satisfy the triangle. The way we do that is by assigning appropriate weights, such that whenever the weight of a query answer is equal to 0, then the endpoints of the path become equal and the triangle closes. Nofar, do you want to give us a summary of what we saw?
Sure. So for direct access, we have a full characterization. The queries that are tractable for lexicographic orders are exactly those that are L-conics and have no disruptive trio. And if we're interested in sum of weights, the tractable queries are the ones where the free variables are contained in one atoms. Now, all cases that are easy for direct access are also easy for selection, but in addition, we show that there are cases that are easy for selection, even though they are not easy for direct access.
For future work, as you can see in the right figure, there are many areas that we haven't explored in this paper, and these are shown with this grid background. And there are also many other interesting questions, such as more expressive queries, other types of orders, or different complexity guarantees. Thank you for listening.
Thank you.